So now we are going to look at the issue how to transmit secret key from the sender to the receiver in network communications. Okay, so let's assume that Alice has a file to send to Bob. Okay, but Alice doesn't want anybody else to read M except Bob. Okay, so that means now Alice wants to use, let's say, use AES encryption algorithm to encrypt M using a secret key K. So Alice knows. So Alice knows how to generate K using ANSI X 9.17 standard or VBS pseudo-random bit generator to generate a 128-bit key. Okay, and she also knows how to use CBC mode of AES to encrypt K. So that creates a sequence of cybertext blocks. So then Alice wants to send this. Let's say, so this C1, C2, CK, CNs really is the cyber block of M. So each of these is 128-bit long. So that means now C1, CN, okay, so Bob gets these cybertext blocks, but Bob cannot do anything about it because Bob doesn't know K. So Bob doesn't know K. So that means Alice needs to send over this K as well. So then the question is, how can Alice send K over to Bob secretly? Oops. Without sharing private, without sharing prior secrets with Bob. Because in network communications, most of the time, we would need to send messages to strangers that who we don't know. For instance, when we do online shopping, so we want to send in our credit card information. We don't want anybody else to see that information, so we will need to encrypt that credit card information and send it to the merchant on their website. But But then we don't share any prior secret that I don't share any prior secret with that merchant that I can use as a secret key to encrypt my secret key, right? So that is a challenge. Okay, so Alice needs to send K over to Bob secretly. So that is the first task. The second is that Alice doesn't share any prior secret with Bob. So that so there is no prior secret with Bob that can be used to somehow encrypt this K. So what can we do? So public key cryptography Pkc was invented to solve this problem. To solve this problem in the 1970s. Okay, so this is it allows key distributions, secret key distributions, secretly, without sharing prior secrets, and it can also be used for digital signature. That is authentication. Okay, so it's commonly used as digital, is commonly known as digital signature. All right. So now let's look at the idea of Pkc. So basic ideas of Pkc. So there are two ideas. So let me talk about the first one. So let's imagine in a postal service. Okay, so Alice wants to send a message M to Bob. And without, so Alice wants to send M to Bob such that nobody else can see M. So the normal method of using an envelope to seal M in it is not secure because anybody who has this envelope can open that envelope and see M. So then what Alice wants to do is to lock M into a box, into a secure box. So this box can only be opened by Bob, not anybody else. The question is, Alice doesn't know Bob, and hence Alice will not be able to send that key to that box. Okay, so there's a box, right? With a padlock. So you lock it and put an M in it. So if Bob has the key to this lock, then only Bob can open this box and nobody else can open it. We assume that this box is a security lock. And if somebody wants to brute force to open this lock, open this box, and then it will explode. Okay, so then M will be gone with the explosion. Okay, so what can Alice do? So Alice figures out a way to do this. Okay, so he asked Bob, okay, to prepare a box. So this is a box with a key latch, okay, and put a, so there is a padlock, and put an open lock. So this is unlock lock. So this is unlock. And put that inside. And keep the key to himself. So this is now called private key, because only Bob has it. Nobody else has it, not even Alice. Okay, Alice doesn't even have it either. So then Alice asked Bob to send this box with a unlock lock inside. So then Alice can put her message M in it, and using the lock, so let's call it B. So this is a Bob's lock. So now let's lock it with Bob's lock and send this over. So when Bob gets it, Bob will use his key to unlock that lock, unlock his lock, open the box and see M. So in this example, we have the following concepts. One, we have the concept of private key. So that is the key kept to Bob himself. Nobody else has it, so that's private key. The other one is anybody else can use it. Okay, and so this is like, so this unlock lock of B is unlock. It is public. So anybody has it can lock it, and then only Bob can unlock it because nobody else has the key. So this is a public, and we call it public key. Okay, and then the box is the encryption algorithm. So you can lock, the way that you have a lock latch, you can use you can apply a lock to secure that box is the algorithm part. Okay, so we have one concept, private key. Second, public key. Third, we have an encryption algorithm. Okay, a box with a latch. Anybody can apply a public key. Okay, so that's a lock. Can use that public key to lock it, and then only the person with a private key to unlock it. Right. So to lock means encryption. To unlock means decryption in this case. So then our question is, how can we implement this idea mathematically? Right, so then we can write code to do it. So this is just an example using the postal office environment, but we need to do it digitally, right? So in order to do it digitally, we have to first make it mathematical. So the answer would be, we are going to talk about public key encryption. So RSA is one of them, right? So this is RSA was published in 19 78. Okay. So now let's look at the second idea. So the second idea is now more mathematical. Okay, so this is the second idea is called key exchange. So that means that Alice doesn't send over a key, doesn't send over a key to Bob. Okay. Instead, both Alice and Bob will send something over and use it to come up with an agreement of a key computed locally. Meaning, Alice computes a key locally, and Bob computes a key locally using the information they exchange, and these keys will be identical. So that is the idea of key exchange. Okay, so now let's see how we can do this. So let's assume we have two functions, f0, f1, such that f1 on f0 x, y can be, so this can be, so x and y can switch the order, they are still the same. Okay, so that is one. And it is hard, computationally difficult, computationally difficult to derive x from seeing f0 of x. So you saw the value of this function f0 on x. You want to derive the input, right? So that is the output. So here, x is the input. f0 of x is the output. From seeing the output, you want to know the input is assumed to be computationally difficult. This means that it takes a lot of time. So this takes, let's say it would take a lot of time, like years or hundreds of years. So we are talking about this kind of time. So it takes a lot of time to do this. Hence, in practice, it is like there is no way to derive your input from seeing the output. So let's say this is our assumption. So now we can use this assumption to realize these ideas. Okay, so now let's see this. So this Alice selects at random and XA. So this is a random number, and keep SA to herself. Okay, SA to herself. And then she computes F0 of XA. Okay. And Bob, that's the same. Selects XD. At random. And keeps it to himself. And then Bob also computes F0 of XB. So then what Alice does is it sends F0 of XA to Bob, and Bob sends F0 XB to Alice. They can do it simultaneously. Okay, so when Alice gets F0, so Alice then computes her key Ka, which is equal to F1. So she gets F0 of XB, and then she knows XA, so that's what Alice computes. And Bob computes KB, which is F1. He gets F0 of XA, and he knows XB. Okay, so that's what Bob computes. And then we know that Ka, we know this function by our assumption, these two can swap, they are still the same. So that means it is equal to F1 of X0, XA, and XB. So this is KB. So that is what Bob computes locally. So likewise, this is equal to, now this two can change. And that is Ka, right? So that is how this can be done. So next time, we are going to provide a concrete implementation of F0 and F1. Okay, so which is a Diffie-Hellman key exchange. Diffie-Hellman key exchange is a concrete implementation of F0 and F1. And we are going to talk about this in the next video.